we are going to do an exercise on capability studies. In this exercise, a manufacturer of a cable wire want to assess if the diameter of the cable meets specifications. A cable wire must be between 0.55 plus or minus 0.05 centimeters in diameter to meet the engineering specifications. Every hour, the analyst take subgroups of 5 consecutive cable wires from the production line and record the diameter. Comment on the capability of the process. So when we talk about capability of the process, we try to understand how efficient the process is with respect to specification limits to understand the production process in detail. We have looked into 3 types of measures. The first one was the capability measure, what we call CP, which measures the width of the specification and the width of the process. We divide it and then we said if it is greater than 1, it is highly capable. If it is less than 1, the process is not capable. If it is equal to 1, then the process barely meets the capability criteria. The second one, what we looked at was capability ratio. And we said capability ratio is a reciprocal of capability, process capability CP. And the third one, what we looked at was CPK, which measures the centering of the process. And CPK is measured as the distance from the lower specification limit to the mean of the process, and similarly vice versa from upper specification limit to the mean of the process, and we take the minimum value. Now we are going to use R in order to estimate the capability of the process. In this example, you have seen that the whatever data every hour, the analyst take a subgroup of 5 consecutive cable wires from the production line and record the diameter. So all the data is arranged in the one column. Let us go down to R in order to understand a bit more deeply as to how to do capability analysis in R. You are seeing here the lower specification limit would be 0.5. Upper specification limit in this case would be 0.55 plus 0.05, that is 0.6 centimeters. So I have opened the R console and now I am going to import the file. And the file, imported file is in the data file, which I have supplied to you. So we go down to import the Excel file. Let us locate the file where the file is located. It's in the Excel file. And the name of the file is capability study exercise. You click on that, the file will get opened up. Now you will see here in the import window that the diameter of all the 100 samples are given in one column. And we said specifically for the package QCC, we require all the data to be arranged in sort of a matrix format. So our first task would be to convert the entire diameter, which is noted in one column, into a matrix. As we discussed for X bar and R plot, the same procedure we are going to follow. Now, first thing is let us create a data frame called as samples dia. Let me share the screen of R. Called samples. First, let me import the file. It's in the Excel file called Capability Studies EXR, and the file is imported. Once you import the file, you would see in the window that all the diameter is located from 0 to 100. And similar way, the group number corresponding to it is also given. Now, let us go down and try to arrange the data in terms of the requirements of QCC, that is in a matrix format, that each subgroup number will have the n number of observation. In this case, there are 5 observations. So let us try to rearrange the data. Let us create a data frame called samples dia, and let us classify it into groups. While doing for groups, you have to mention where is the data. So data equal to the name of the file here is capability studies exercise. And we have to give where the column is, the data is located. The data is located in the first column diameter. Then we are going to give the subgroup size, which would be available in the sample. So again, we have to give the name of the data file and the subgroup name. Now, after doing that, when you press enter, you would see here. Let us now examine how this particular data is reorganized. Now, when you look at this, earlier it was all in one column. Now you can see there are 20 sub-samples being taken and 20 samples being taken. And in each sample, you will have here sub-sample of 5. 1, 2, 3, 4, 5. Now, this data can be used in order to classify it into data so that we can do a capability study. So after doing that, let us now try to calculate the control limits of the X bar and R charts and so on. So for that, we are not going to plot it, but rather this feature will help us to make a data frame with those specifications which are required for calculating the capability studies. The specification like what would be the control limit of the process, what would be the upper control limit, what would be the lower control limit, and so on, would be computed by this particular command called as QCC. So now let us create a arbitrary data frame called capability cap.diameter. And then let us now store this value of the QCC command into it. For QCC command, you have to first give where the samples are located. In this case, samples are located in the particular data frame called samples.dia. And then we want to give what type of chart we are using in order to measure the capability studies. We are here using the X bar chart because you have samples more than one, subsample more than one. So let us give type and then write here X bar. After that, we know the target in this case. The specification limit varies from 0.55 plus or minus 0.05. So that means in this case, the target is we have to de-engage the plot. So plot, we don't want the plot here. We just want to have the commands given into it. So now if I see what is stored in capability diameter, you will get to know that it has calculated things like what are the various the data in terms of sample sizes. It has also calculated what is the standard deviation of the process, what is the center line of the process. The limits are also been given like 0.5 to 1, 0.72 and so on. Now we are not going to use this data, but rather we are going to use these data in order to establish the or estimate the process capability. So for that, we have a command called as process.dia, process.capability. And we have to give them, give in this, you have to give the where the data is located. Now the data is located in the earlier one. Here it is called CAP dia. So we will give the name of the command. It should automatically appear. The data is located. Now we have to give the specification limit in order to calculate the capability. Let us give the specification limit. The specification limit is given by the command spec.limits. And then when you press that, you have got already the particular command getting engaged. Then we have to give here the lower specification limit is 0.55 minus 0.05. So the lower specification limit would be 0.5. And the upper specification would be 0.55 plus 0.05. So it would be 0.6. And now we have to give what is the target value of the process. So target in this case is 0.55. Now you will see a plot with a graph. Now you can see here a graph here appearing. And in this graph, it is clearly shown that the number of observation is 100. The target was 0.55. The center line is what you are seeing in the dotted line. And the lower specification limit and the upper specification limits are already given. And now you would see here in this that the number of observation is 100. The center line of the process is 0.54, whereas the target was 0.56. So some percentage of the defects will be here lying down here and there on the less than lower specification limit and upper specification limits. We are also seeing the standard deviation 0.019. So based on these data, the software has already calculated us the capability of the process, which is 0.875. And the lower, to calculate CPU, we said it will measure the distance from the lower specification to the mean of the process and divide by the standard deviation, that's 3 sigma. You are getting CPL as 0.813, CPU as 0.937, which is from the upper limit. Since if you remember, the mean of the process is 0.55, whereas the mean of the process is 0.54, whereas the target is 0.55. So there is a slight shift towards the left-hand side. So you can see a higher CPU on the 0.937 compared to CPL. So you can see the width from the existing process mean to the upper specification limit is quite high. That's why you can see here 0.937. However, since we are taking the minimum value, so this will not have any impact. That's why 0.813 and 0.91937, the minimum value would be 0.81. And also when you look at here on the right hand side, you would see the expected number of observation based on the normal distribution would be 0.73%. Whereas expected number of defects, which is going to be from the upper specification limit, would be 0.25%. Similarly, if you examine the data, the observations from lower specification limit would be 1%, and the upper specification limit, the number of defects which are observed would be greater than 1%. So from this, we would say the process is not capable because the CP value is 0.875. It should be greater than 1.33. And if it is 1 and above, that means the process barely meets the capability of Similarly, if you look at the CPK value also, it's 0.813, which should have been 1.33. And from this data, you can say that the process is not capable to meet the specifications of the customer. That means we have to improve the process. Let us calculate the amount of defects if 1 million parts were being produced. So at that time, what we do here is, we know here the expected value is 0.775. Let us now calculate what would be the value at this particular level. So we can see here that if I multiply 0.74 multiply by 10 raised to 4, why 10 raised to 4? Because this 0.74 is in percentage. So when I remove the percentage sign and multiply by 10 raised to 6, 2 zeros will get cancelled and you will get the answer corresponding to the lower specification limit. You will get around 7,400 defects. Now let us calculate from the upper side how much defects would be there. And let us see this number will be lower because the width from the mean of the process to the upper specification level is higher. That is why the number of defects are less. So similarly, the observed value in this case is just 1% of both the examples. So this is just to indicate that from the expectations for this particular process, what would be the amount of defects. Now you would see here the total amount of defects which would occur due to both the process being above the upper specification limit and lower the specification would be 9,900 defects per million opportunities, or per parts per million which are being manufactured. So out of 1 million parts, 9,900 would be defective for this particular process. So if a problem comes in the examination, you have to specifically plot the curve, measure CP, CPL, CPU, and observe these values CPL, CP, CPL, CPU, and CPK, and then comment both on process capability CP if it is greater than 1, barely meeting if it is greater than 1.33, that means the process is highly capable. Same is the case with CPK. If it is greater than 1.33, then the process is meeting the targets.